Okay, today we're going to be proving why square root 2 is an irrational number. And we're going to be doing this using a proof by contradiction. And if we wanted to start with a proof by contradiction, the first thing we need to do is we need to assume that root 2 is actually rational. So what we're going to try and prove, so RTP stands for right to prove. We have the right to prove that square root 2 is rational. So that's how we start off any proof by contradiction proof. And the way we show that something is rational is we can show that it's equal to sum p over q, some fraction p divided by q, where p and q are both positive integers. In this case, we're going to say they're positive integers. And we're also going to say that p and q are coprime. And what coprime pretty much means is q and p, they share no two factors whatsoever. They share no prime factors whatsoever, more specifically. So there's no situation where I'd get 8 divided by 4, and I can cancel these out to get 2 divided by 1. There'd be no such case of that. I'd never get something like this. Okay, now continuing on with this, here's how the proof goes. The proof goes that I can square both sides of the equation in this line here. So square root 2 squared is equal to p squared divided by q squared. And square root 2 squared is simply just 2. And I can multiply both sides. In this equation, I can multiply both sides by q squared. And in doing so, I'll get that 2q squared is equal to p squared. And now what do we notice here? We've noticed that p squared is written as 2 times another constant q squared, where q squared is just some constant, right? So if I can write p squared as 2 times another number, that means p squared is divisible by 2. Is divisible by 2. But now looking back on this, didn't we also say that p had to be a positive integer? So in order for p to be a positive integer, that means p squared has to be a positive integer. That means when we square root p, we cannot get some decimal answer like 6.2317 or something. We have to get an integer. And the only way that p can be an integer is if p is also divisible by 2. And you can check this out for yourself. If I were to square root the number 4, that's simply equal to 2. If I were to square root the number 16, that's equal to 4. If I were to square root the number 36, that's equal to 6, and so on and so on and so forth. If p squared is divisible by 2, then p is divisible by 2. So that means I can write p as sum 2k, where k is just some random integer, right? Because p is even, it can be written as 2 times another integer. And the way I can say this is, I can also say k is a positive integer. Now continuing on, we have this line over here. At the very top of our screen, we have 2q squared equals to p squared. So I can simply replace the p that's over here. I can replace this p here with p equals to 2k. I can replace the p with 2k. So what I'll get is 2q squared is equal to 2k in brackets whole squared. Now expanding this out, we'll get 4k squared. That means that 2q squared is equal to 4k squared. And I can simplify this by simply saying that q squared is equal to 2k squared by dividing both sides by 2. And what do we have here? We can see that q squared can be written as 2 times another number, another constant. So that simply means that q squared is divisible by 2. And again, by that logic, if q squared is divisible by 2, that means that q is also divisible by 2. We have a contradiction, and you may be wondering, where is our contradiction? Here is where our contradiction is. We have said that both p and q are both divisible by 2. But didn't we say in our original assumption that p and q were both coprime? And coprime pretty much means, to reiterate, coprime means that p comma q, they both share no common prime factors. And as you can see, we have showed that they do have prime factors. So in the process of trying to show that root 2 is rational, we got some absolute mathematical nonsense. We got that q is both divisible by 2 and p is divisible by 2, and they are also coprime. That makes absolutely no sense. So in the process of trying to prove this, we have shown it's not possible, and hence, in the process of trying to prove the opposite, we have just proven that the original statement is true, because we have failed in trying to prove the contradiction.